Okay, so the final thing that we have to see in our revision is what are the components of load torque. In equilibrium, the motor torque must be equal to the load torque. Okay. The motor must be able to generate sufficient torque so that it meets the load requirements. Now, when we say that this motor torque is equal to the load torque, what is included in the load torque? Who can answer? Or what are the components of load torque?
Sir, hello.
Yes, Shiva.
Yeah, low torque,
Frictional torque.
compression low torque, inertia,
Hmm.
torque due to inertia,
Hmm.
torque due to friction,
Hmm. Yes.
and windage.
Okay. Anything else? Yeah, keep your speaker off. Yes. Any other components? Shiva has said three things: inertia, friction, and windage. Any other component?
Sir, own weight of the load.
Yes. The torque required to do the useful work, and or torque that is required by the load itself. Okay. So broadly, there are three components actually. One is the major component will be the torque that is required by the load. The second one will be the windage torque. That is the torque required to overcome the opposition due to wind. And the third one is the friction torque. And this torque due to inertia comes inside friction. Okay, Shiva? That is known as stiction. Static friction. Static friction or stiction. So friction torque includes the torque due to inertia, and actually friction torque has three components. So one is the torque due to static inertia. The second is a component that varies linearly with the speed, and the third component is the component that varies at the square of the speed. But the function that varies with the square of the speed is negligible. So mainly you have inertia and a component that varies linearly with the speed. If you neglect inertia, then friction torque will be directly proportional to the speed. Okay, is this clear, everyone? Yes or no? That is Sumit.
Yes, sir. Yes, sir. Hello.
Yes, yes.
Yes, sir.
So the component of friction torque that varies linearly with the speed, that is called as viscous friction. But the major component of the friction torque is viscous friction. You can neglect inertia in some loads, but in some loads, inertia plays a very, very important part, such as in traction loads. Okay.
So one another thing was there, Coulomb friction.
Yes, Coulomb friction varied with the Coulomb friction was constant, not varied with the square of the speed. It was constant.
Yes, sir. It is constant.
Constant. Okay. So overall, the load torque contains three components. One is the torque required to do the useful mechanical work. Second is torque required to overcome windage. And the third is torque required to overcome the friction. And this friction torque includes three components. One is the static friction, which we know otherwise as inertia. One component is viscous friction that varies linearly with the speed. And one function is Coulomb, Coulomb friction that is constant irrespective of the speed. Okay, so that finishes our review, and now we start with EE1012 machine drives 1. There are a lot of good books available for machine drives. Lots and lots of books are available. But here at Durgapur, the professor who taught before me, he used to use a book called Chilikin, M. Chilikin, CHILIKIN. So when I was given the subject, I also went through that book and I was amazed by that book. That book has things which no other books have. If you take today's books, you'll find that the subject matter is same, only the language and presentation is different. But the book by Chilikin has remarkable things, and the approach to the teaching is also remarkable. The only problem was the book was very old, so is now out of publication because modern drives you cannot teach from Chilikin. But the basics I am going to teach from there. As I told you, till mid-semester, we are going to follow the book by M. Chilikin. I have the soft copy. If anyone wants, I will share the soft copy in the WhatsApp group. Okay. So the first topic today that we are starting is speed torque characteristics of electric drives. Now, whenever we are asked to design a motor drive system or an electric drive system, what we are given is the load requirements in terms of the load, speed torque characteristics. So the first thing that we have to do is we have to find a suitable motor that will be able to impart the speed torque characteristics to the load. Apart from that, during transient conditions, how the motor will behave, such as transient conditions such as acceleration, braking, speed change, speed reversal, how the motor or how the system will behave, that depends on the speed torque characteristics of the motor as well as the load. So it is essential. Whenever you study drives, the first thing that you study is speed torque characteristics of motor, whether it be basic drives or whether you have advanced drives. The first thing that you have to do is study the speed torque characteristics of electric motors. Now, the normal approach of teaching the speed torque characteristics is they start with the basic machine equations and then they draw the speed torque characteristics. But as I told you, Chilikin has a different approach. Okay? So he has given a basic equation from which the speed torque characteristics of all motors can be derived. Okay. So the speed torque characteristics of some machine or mechanism, the speed is given by omega and it is a function of the load torque. And in this case, we draw speed torque characteristics for transient conditions or steady state conditions. Yes, anyone? Speed torque characteristics are drawn for transient conditions or steady state conditions.
Steady state condition.
So for steady state condition.
Steady state.
Steady state conditions. And under steady state, okay, at equilibrium, the motor torque will be equal to the load torque. Okay. The speed torque characteristic of the motor, machine or mechanism is given by omega is some function of TL. Where TL is the load torque and implies the torque developed by the motor to meet the torque requirement of the load. And how do we define the speed torque characteristic? It is the relation between the speed at which the machine is operated and the resisting or load torque it develops. Okay. So basically, you have a graph where on the x-axis we are going to have the motor torque or the load torque, and on the y-axis we are going to have the speed. So here we are taking the load torque or the motor torque as the independent variable and the speed as the dependent variable. Or here we are plotting the speed as a function of the load torque. Jairam has joined. Jairam, was your problem solved?
Sir, actually, my network is low, sir.
What is your roll number? What is your roll number?
19, sir. 19, sir.
19. Okay. Okay, so different kinds of machines and mechanisms exhibit different speed torque characteristics. However, as I told you, Chilikin has given a basic equation based on which we can, in general, derive the speed torque characteristics of majority of the machines. So I have shared this equation with you on WhatsApp. I'm going to show the equation here. Okay, I have to present the screen for that. Okay, can you see the equation?
Yes, sir. Yes, sir.
So this equation, the equation is given as TL is equal to T0 plus bracket TRN minus T0 bracket closed, then in bracket omega upon omega n bracket closed to the power x. I take this as equation number 1. So we have to know what are the terms here. First of all, TL. TL is the gross resisting or load torque developed by the unit at speed omega. Omega is the speed of the motor in radian per second. T0 is the resisting torque developed by unit due to friction in its moving parts. T0 is resisting torque developed by the unit due to friction in its moving parts. TRN is the resisting torque developed by the unit when it is driven at its nominal rated speed omega n. Omega n is the nominal or rated speed of the motor. Again in radian per second. Omega is the actual speed, omega n is the nominal or rated speed of the motor. So TRN is the resisting torque developed by the unit when it is driven at its nominal or rated speed omega n. And x is an exponential coefficient characterizing the change in resisting torque with change in speed. Okay, is the equation clear? Everyone?
Yes, sir.
What is TL?
Sir, please repeat the x.
X is simply a coefficient, okay, that will characterize.
So is this a general equation which is given in Chilikins?
Yes, this is a general equation, and for different motors, the value of x will change. Okay, for different
So
machines,
what is omega
for
n?
mechanisms. Omega n is the nominal speed or rated speed of the motor.
TRN, sir.
TRN is torque at the rated speed. Displacing torque developed by the unit when it is driven at its nominal or rated speed omega n. Okay. T0 is torque due to friction in its moving parts. Okay, clear? I think you can write down this equation somewhere.
Sir, T naught is low torque.
EL is the load torque. EL is the load torque. T0 is T naught is the torque required to overcome the friction. Okay, can I move forward? Okay. Okay. So based on the value of x, we can have different types of speed torque characteristics for different machines or mechanisms. Now we are going to see 4 types here. Okay, you've written the equation because you will need it probably. So we are going to see 4 types of speed torque characteristics based on this equation. Okay. The first one is characteristic that is independent of speed. That is the straight line, vertical straight line given by characteristic number 1. Now for this characteristic, if you see the equation, the value of x is equal to 0. Okay? If you put the value of x is equal to 0, then TL becomes equal to T0 plus TRN minus T0. Correct? T0 also get cancelled. So the load torque becomes constant irrespective of the speed. So that is characteristic number 1. Is this clear? What I just said?
Yes, sir.
Yes, sir.
In this equation, if you put x is equal to 0, then the load torque becomes constant irrespective of the speed. That is your characteristic number 1, where the load torque is constant, whatever may be the value of speed. Such characteristics are exhibited, for example, by cranes during hoisting. And when a crane is lifting up or hoisting a heavy load, what is the major component of the load torque? Anyone?
Sir, initially it is well, due to inertia, means
Torque required to do
it is
full
lifted
work.
by some jerk, means when it is crane is lifting something.
Okay, let me make one thing clear. We are neglecting inertia from now on. Okay, is this clear? When we are drawing these characteristics, we are neglecting inertia. We are not considering inertia. Okay, inertia is for a very small duration, so we are neglecting it. Except in loads where inertia is a very, very big component, such as in cranes. In cranes, you cannot neglect inertia. But in cranes, you cannot neglect, but in cranes, you can neglect inertia. Okay? Okay, so I repeat my question. When a crane is hoisting a heavy load, what is the major component of load torque?
So wait, sir.
Some more.
Weight of the load,
It's a friction torque. Torque required to do
friction
full
torque.
work.
So the motor
Torque
torque.
required to do useful work.
Yes, sir.
So the motor torque.
Friction. At what speed does the crane pick up the load, hoist the load?
Low speed.
Very low speed. Friction is negligible at that speed. Okay? We just seen friction torque is directly proportional to the speed. So at that low speed, friction is negligible. What is the major component? It is the torque required to do the useful work. And that torque required to do the useful work in case of crane is heavily dependent on the gravitational force. Is that correct?
Yes, sir.
Yes, sir.
Yes, sir.
And does the gravitational force change with the speed?
No, sir.
No.
No, sir. Not dependent on the speed.
Yes. That is why in case of a crane hoisting a heavy load, the load torque is constant irrespective of the speed. Okay. So in this type of mechanisms, we'll find that the load torque is constant. Torque required to be developed by the motor is also constant irrespective of the speed. In case of low speed mechanisms, you can say that in applications where the major torque is the friction torque, there also you will get similar speed torque characteristic. Okay. Especially if the speed is constant. If the speed is constant, friction torque will be constant. So in that case also, the load torque will remain constant. Okay. Let us come now to the second characteristic. For the second characteristic, what will be the value of x here? This second characteristic that you are seeing, linearly rising characteristic. What will be the value of x? Yes, the value of x will be equal to 1. Okay. So that the load torque becomes directly proportional to the speed. Okay. You have to remember that omega n, that is the weighted speed, is constant. Okay. When you put x is equal to 1, the load torque becomes directly proportional to the speed, so you get the characteristic number 2. Here the load torque is rising in direct proportion to the speed. For speed is, the load torque is rising in direct proportion to the speed. Have you seen this type of characteristic? Anywhere?
Yes, sir.
Where?
Sir, fan, sir. Fan type load, sir.
No, no. I'm talking about curve 2.
So locomotives or electric vehicles.
Locomotives driven by electric vehicles. No.
No.
One example is a DC generator connected to a load of constant resistance. Okay, there you will see this type of characteristic. Whereas the speed is increasing, the load torque is also increasing. Okay, is this clear?
Example, repeat, sir. DC generator connected
DC generator connected to a load of constant resistance, constant ohmic resistance. Think about it, you'll find. In case of a DC generator, if you increase the speed, what happens?
EMF increases.
Yes, if you increase the speed, what happens?
Sir, EMF increases.
EMF means increase.
Yes, the generated EMF will increase. And if the generated EMF increases, the value of current will also increase proportionately, and especially because the load is constant. And if the current is increasing, in case of DC generator, torque is proportional to the armature current. So if the current is increasing, the torque is also increasing. Okay? Yes or no?
Yes, sir. Load torque is proportional to I square.
Yes, sir.
No, load torque is not proportional to I squared.
Oh, load torque.
Separately excited DC generator, not series. Separate or shunt.
इतनी excited DC generator जो होता है तो क्या होता है लोड कैसे पता करेगा
Yes.
समझ होता है बीमा चाहिए और लिखते हैं हम तो
Hello.
हाँ yes sir.
Load torque is the independent variable.
Load torque is independent variable, yes. In this case, here when we have drawn, we have considered load torque to be the independent variable, but actually if you see the load torque is the dependent variable. It will depend on the speed, especially in case of DC generator. If you change the speed and the DC generator, the speed of the generator is determined by the prime mover. Okay, so that is within our control, and the load torque will then depend on the speed. Okay. Okay, can I move forward?
Yes, sir.
Okay. Third type of characteristic, that is the non-linear rising or parabolic characteristic, that is curve number 3. Again, what will be the value of x for this characteristic?
Sir, 2 parabola.
It will be 2. So in this case, the load torque will be a function of the square of the speed. Okay. Actually, the problem is, I'll tell you what is the problem. The problem is that this diagram, both the diagram and the equation are taken from the book, but the diagram and the equation are not matching. In the equation, omega is the independent variable and TL is the dependent variable. But when he has drawn the diagram, he has taken TL as the independent variable and omega is the dependent variable. And that is why the problem is coming. But I think why he has drawn it like this is to better depict it, probably. But in actual practice, omega is the independent variable and the load torque is the dependent variable, as is seen from this equation also. Okay. Sure. So if you put the value of x is equal to 2 in this equation, you get load torque as a function of the square of the speed. That is the curve 3 shown in this diagram. Where do you see this type of characteristic? Torque proportional to square of speed.
So fan.
And the fan.
Yes, fan type of torque. So somebody had
Compressor.
said that curve 2 is fan type. No, curve 2 is not fan. Curve 3 is for a fan type of load. Or we say that
Yes, sir. Yes, sir.
machines which exhibit characteristics such as 3 are known to have fan type speed torque characteristics, because fans develop a load torque that is proportional to the square of the speed. Similar torque will be developed when you replace air by water. That is why centrifugal pumps also have the same characteristic. Ship propellers also will have similar characteristics. Is this clear?
So centrifugal pump means which type of characteristics they follow? Centrifugal pump?
Curve 3. They have characteristics similar to fan. And in fan, the major component is to overcome opposition due to air. And in centrifugal pumps, it is due to the water. Okay. Sure. The last characteristic, curve number 4, non-linear falling characteristic. What is the value of x now?
Minus 2.
1.
Yes, the value of x is equal
Sorry,
to
sir. Minus 1.
minus 1. If you put x is equal to minus 1, torque will be inversely proportional to the speed. Okay? You get curve number 4. Now tell me, if torque is inversely proportional to the speed, what happens to the power?
Constant power, sir.
Yes, the power remains constant. But power is proportional to the product of torque and speed. So in the characteristic given by curve 4, as the speed is increasing, the torque is decreasing. Or as the speed is decreasing, the torque is increasing, so the power remains constant. Okay. Characteristics of this type are exhibited by certain lathe machines, LATHE, boring machines, etc. Okay.
Sir.
Yes.
So when a machine is run over synchronous speed, then this kind of behavior is shown.
No. Which machine? Which machine? Which machine?
Sir, I have seen somewhere in BTech, sir. I can't remember the exact which machine.
See and show me, that I'll tell you. Okay.
Induction generator.
Okay,
Induction generator, torque speed characteristic.
Above the synchronous speed, he's asking me, I think so. Induction generator.
Let me go back. Let me ask you. Which characteristic will be shown by induction generator? 1, 2, 3, 4. Can you see the diagram, Sumit?
Yes, sir.
Which characteristic will be shown by induction generator? 1, 2, 3, 4.
Fourth one.
Hmm?
Fourth, sir.
4. Yes, anyone else?
3. Parabolic.
3, sir.
3.
4, sir.
4. As torque increases, speed decreases. Means as speed increases, torque decreases. Speed increases, torque decreases. Sorry. Torque as speed increases, torque decreases.
Hello,
4.
Anyone else?
sir.
Hmm.
Sir, in induction generator, how torque we plot load torque.
क्या बोल रहे थे वो सिंह अभिषेक?
Yes, sir. So in induction generator, we generate electricity, right? Then where we can plot torque, load torque, and something like that.
It is a rotating machine. The torque is there.
Yes, sir. But
The torque
in
will
graph,
depend on the electrical load. Induction generator also has a speed torque characteristic. ऐसा नहीं कि नहीं है.
Second equation.
DC generator, do they not have a speed torque characteristic? Second one. Shiva is saying second.
Sir, 2, sir.
Okay, I'll tell you what is the answer. And then you have to explain the answer to me in the next class, that is tomorrow. The answer is very close to 1. The answer is very close to 1. Not 2, not 3, and not 4. Definitely not 4. But depends on where you are operating the induction motor. Okay? So the question is, depending on where you're operating the induction motor, and generally it is operated in the stable region, the speed torque characteristic of the induction generator will be very, very close to 1. Justify this statement. That is your assignment for tomorrow. Okay? Yes or no?
Yes, sir.
Yes, sir.
Okay? It is not 2, it is not 3, and it is definitely not 4. It is very close to 1. Okay. Start tomorrow's class from here. Yes, Priya, you want to say something? I am stopping the recording. Huh?
So means one characteristic I have to write why one character.